So, a couple things here. All right, so this is really just about solving systems. Both of these last two sections go together. We're going to start off with linear systems. I'm going to do just a brief review, and I don't want to spend a lot of time on this because you've done so much of this. You did this a lot in Algebra 1, and then last year in Geometry, you should have spent some time at the beginning of the year going through this. And I know if you were in my geometry class, we did this during the geometry class throughout the year, and so you're going to be, I think everyone's going to be pretty clear with how to do this stuff, but let's take just a second and remind ourselves how this all works. If I want to solve a linear system like this, and I'm going to call this a 2x2 linear system because there's two equations and two unknowns, or two variables, right? What are our two strategies for doing that? There's two different ways that you guys would have talked about doing that in the past. What's one strategy? Don't be afraid to be wrong. Remember how we did these things?
What?
There's two different. Do you remember that there was?
Yeah, you put it in for y.
Okay, substitution. There you go, substitution. Okay, one way we can do this is by substitution, and that's a real common way to solve any system, would be by substitution. So you use substitution, remember, when either a variable has already been isolated, like it has here, or one of the variables is very easy to isolate. And what makes it easy to isolate? If its coefficient is 1 or -1, then it's really simple to get by itself. But otherwise, it could be a little trickier. So those are the cases when substitution would make sense. So in this case, it's a slam dunk. Substitution for sure, because it's already, second equation is already solved for y, right? Y is already isolated. When you're solving by substitution, always put a box around the substitution equation. That's my hint, because you're going to come back to it. And so what this means then is, because I've solved for y in the second equation, that's the substitution I'm going to make into the first equation, right? So what does the first equation become then? -4x minus 7 times y, but instead of y, we're substituting x plus 1 equals -84, right? And that's simple from there, right? I've only got one kind of variable there now. By substituting for y, we've eliminated the variable y from the equation, and now we've only got x to deal with, which makes it simple. What are the steps to solve this then? What would I have to do first before I can isolate x? Yeah, I got to combine like terms. I got to distribute the -7. So I get -4x. What's that going to give me when I distribute the -7? -7x minus 7. And then I just combine like terms, right? -4x minus 7x is -11x. I'll add 7 to both sides. What do I get on this side? What's that? -77. Right? And then last step? Divide by -11, right? And then I get x equals 7. Okay, now what? Yeah, I put a box around the substitution equation, so I go right back to the box, right? And plug in that value of 7. So what do I get for y then?
Y equals 8.
Yeah, good. 7 plus 1, which is 8. Good. And so we're going to enter the answer as an ordered pair of the form xy. So the answer is 7, 8. Okay, so talk to me about that solution. We just we did a little review here, but what did this all mean? What does that represent, that solution? A point. What unique point does it represent? You're right. What point does it represent? If I were to graph each of those equations, what would they look like? Bottom one's pretty easy to see. What form is that in? Y equals mx plus b. What's that the equation of?
Slope.
A slope-intercept. That's a line, isn't it? The top one is a line too. It's in standard form. How do you know the top one's a line? Well, the way I like to think about it is, could I, if I wanted to, put the top one into the form y equals mx plus b? Yeah, I could, right? I could add 4x to the other side and divide the whole right side by -4. And if I did that, when all the dust settled, wouldn't I have something like y equals some fraction times x plus some other number? So it would be mx plus b, right? So it is a line. They're both lines. And what's interesting about that point right there? That's where they cross, right? So when we solve a 2 by 2 linear system, graphically what that means is, how do those two lines interact? Well, these lines intersect at that point, right? Without thinking graphically, just in general, when we solve a system of equations, we're trying to find the values of the variables that make both of those equations true at the same time, right? Okay, that makes sense? So that was the substitution strategy, right? What about something like that? Actually, we could use substitution there if we wanted to. It'd be a little bit cumbersome. We could.
Could you multiply them?
Yeah. What's the other strategy we have for solving linear systems? Substitution or what? Remember? I know y'all did this. What was it?
Oh, I don't know. What's the time?
Okay. Linear combination. Maybe somebody called it elimination method? One of the two. Either one, linear combination or elimination, doesn't matter. What's that one do though? That's the one where we want to try to multiply one or both, if necessary, of the equations by a number so that when we add them together, either the x's or the y terms will cancel, right? So when they line up vertically, we want the x's or the y's to cancel, right? So what would I have to do here to accomplish that? Multiply what? Bottom one by 2, yeah. So here's how I like to show this. And if you had me last year, this will look pretty familiar. The way I like to show this, I think is a good way of doing it. If I'm going to leave an equation alone, I just draw a straight arrow, which means that one's going to get dragged over there without any changes. So that equation's going to stay as 4x plus 3y equals -6. But the bottom one, we were going to multiply a 2 through both sides, distribute it through both sides. So I'll include a 2 in the middle of that arrow. So what's that going to give me for the bottom equation then? -4x minus 4y equals 4. And then when I add those up vertically, sure enough, the x's cancel, right? What happens? 3y plus -4y is -y, and then -6 plus 4. So then what's y? 2. I multiply each side by -1 to get rid of the minus. Everybody agree? Or divide by -1, same thing. Everybody agree I get y equals 2? That's half the problem. Now where do I go to find x? Go back to, either one of those original equations I can go back to, whichever one seems easiest. I'd say the top one because they're positive coefficients, yeah. So if we plug 2 in right there, we'd get 4x plus 3 times 2 equals -6, right? So what's that give us? 4x plus 6 equals -6. What are the 2 steps in order to get the x by itself there? Good. Subtract 6 and then divide by 4. Very good. All right. Okay, so that gives us 4x equals -12. So x equals -3. So it's the ordered pair. Remember, x goes first. -3, 2. That's it. Okay. Now, we don't have to take time to do the whole problem, but let's just, which strategy is clearly going to be the one that we'd use here? The elimination one. Good. So we don't have to do the whole thing, but let's just at least practice setting it up. What numbers am I going to multiply the equations by here? There's no one answer, but there's probably one best answer. You want to keep the numbers as small as possible. So the top one by... Oops. I'm not gonna be able to multiply just one equation this, I'll have to multiply both, aren't I? Top one by 5, okay. And the bottom one by 2, good. That's gonna work, because that's gonna give me 10x and negative 10x, right? Everybody see that? How do we get those numbers? Well, worst case scenario, just multiply, the 5 comes from what the bottom, that's the factor in the bottom equation, the coefficient. The 2 is the coefficient in the top equation, right? So I know that 5 times 2 must equal 5 times 2, right? What do I get when I distribute the 5 all the way through the top? 10x. Good, minus 25y equals, good, and the bottom one, negative 10x, what, minus 12y equals negative 76. And sure enough, the x's cancel, and I could do it from there, couldn't I? Right now I've got negative 37y equals, what is that, negative 111? Okay, and so then if I divide each side by negative 37, that just what gives me 3. Right? So I can just plug that back into one of the original equations and find x. Might as well do it, we're almost done. If I plug it into the top one, 2x minus 5 times 3 equals negative 7. So 2x minus 15 equals negative 7. So if I add 15, 2x equals what? 8. So what's x? Okay, so the solution would just be 4, 3. Okay? So that's a quick review. You guys have done all that stuff many, many times in the past, but it's been a little while. Actually, I want to show you just two more quick examples where something strange happens. What about this one? What could I multiply bottom one by here? 3. Top one we'll leave alone. Bottom one by 3. So that's going to give me what on the bottom? 6x plus 15y equals negative 72. What happens when I combine these? Yeah, everything cancels. So like those cancel, those cancel, those cancel. So what do I get on the left? 0. What do we get on the right? Okay, what's that mean? Okay. There's two possibilities, aren't there? Now let's think about the ways that two lines could be related to each other or interact. We've already talked about one way, which is if they intersect, right? They could intersect once. What else could they do? So what would that look like graphically? Infinite solutions, what would that look like? Okay, so let's say here's one line and there's the other line. It's supposed to be right on top of it. Right? If they're the same line, yeah, if they're the same line, then they're going to have infinite solutions, right? What's the other way though? How could they have no solutions? If they're parallel. Right? If they're parallel, they never cross, right? So there's two possibilities other than a single solution. Well, whenever the variables drop out of the equation like that, it means it's not a single solution. It's going to be one of the other two. Which one is this going to be? You got it. Infinitely many. Yeah, and here's why. Here's all you have to ask yourself. The equation that we were given when the variables dropped out, is it true? Is 0 equal to 0? Yeah. That's always true, isn't it? So that represents, there must be the same line. There's an infinite number of solutions then. So if you're given a true equation, infinitely many solutions, right? Compare that to one like this. This is just a substitution equation, right? I could just substitute the bottom y into the top y, right? And so I'll substitute, instead of a y up there, I'll get a negative x minus 11. If I add x to both sides, look what happens. I get negative 11 equals negative 6. Okay, the variables dropped out, but is that true? It's never true, so that means parallel lines, no solution. Okay? All right, so now calculator time. I want to show you a trick for quickly solving linear systems using your calculator. Not that you can't do these algebraically, but a lot of times in real life we want to get an answer quick, right? Here's a way to do it. So I like to call this just solving equations into the calculator, or isolating for y into the calculator. Let's look at what the steps would be if I wanted to solve for y in that top equation. What would the steps be in order that I'd have to do? What's the first thing I do? There's my original equation. You guys know this, reverse order of operations, right? You can do this, is no big deal. So you're gonna, well, okay, I have a negative 2x, so I'm going to subtract negative 2x or add 2x to both sides. So step 1 is gonna be add 2x to both sides. So I get negative 2y equals negative 20 plus 2x, right? What's step 2? Divide by negative 2. There's never going to be more than 2 steps if you're isolating, if they're linear equations and you're solving for y. It's always going to be, at the most, those 2 steps. That's it. So how could I break those down into a process for the calculator? Well, let me ask you this. How would I enter that if I'm not going to use the fancy fraction template on the calculators, which I actually recommend you don't use? For one thing, it's really tiny, it's kind of cumbersome to get to, and when you solve the system, it'll give you back fractional answers, and you actually don't want one this time. I want you to round to the nearest hundredth. So if I wanted to enter that as a string in the calculator, how would I do that? How could I ask the calculator?
Y equals 10 minus.
Okay, but without simplifying. If I just want to enter it just like that. Okay, so how would I write it out, though? How would I write this part out? What's wrong with this? If I just enter those keystrokes, what's wrong with that? I need parentheses, because the calculator's only going to assume that I'm dividing the x by negative 2, right? Everybody see that? The way I would do that on the calculator is, or I would need to tell the calculator that it's that whole thing that's being divided by negative 2, right? Okay, and so what are those red parentheses really, what are they encompassing? They're just containing the numerator of the other side, aren't they? And that whole thing is being divided by whatever the coefficient of y was. Agreed? So then here's our strategy. If we ever want to just isolate a variable into the calculator, like let's just say we're going to isolate that y in the top equation, what could we do? Well, we'll go to the y equals screen, and we'll always start off by just opening up a set of parentheses for whatever's on the other side of the equation. So what's opposite the y? Well, we're going to start off with a negative 20. What do we have to do to get rid of this term to the other side? Come on now. How do I push that negative 2x over there? What do I do? Add it. Good. So I'm going to add 2x to the right side, and then I got to close the parentheses because now I'm going to divide the whole thing by negative 2, right? So there it is. Open a set of parentheses, start with what you've already got there, add or subtract to get the x term to the other side, close the parentheses, and divide by whatever's in front of y, coefficient of y. Don't simplify. The calculator can deal with that just fine, right? If you try to simplify it, you're opening up an opportunity to make a mistake. Just leave it like that. So what about the bottom equation then? What am I going to do there? Tell me what I push on the calculator. What's the first thing I'm going to push? Parentheses. If I want to put a 0, I can. I don't need to, but I can. Minus. I'm trying to solve for y.
Oh,
Plus 4x. Close parentheses. And divide by 2. Good. And then there they are. So I want to find the intersection graphically, so now what do? Hit graph. If I hit graph, I'm at the mercy of whatever the window was like last time, right? So maybe a first thing to always try is just zoom standard. And if I'm lucky, I'm going to be able to see the intersection there, which I can this time. And then all I have to do is find the intersection, right? Once I can see the intersection, all I have to do is just go second calc, which one? 5. Second calc 5, and then triple enter, and that's it. One enter is to tell the calculator that's the first line, second line, and then a guess. Do I even have to bother moving the cursor to make a guess here? I don't, because how many total solutions are there? 1, so the calculator can't find the wrong solution. When it finds a solution, it's got to be the right solution. So just second calc 5, triple enter, and it gives me the answer. Okay. So if I round that to 3 decimal places, it's just 3.33, 6.67. Okay, but what if it's off the, or what if I don't see the intersection? What's going on? Off the window somewhere, right? Does that make sense? What if the intersection had been like up there? Then I wouldn't have seen it in that small window. So what do?
Zoom out.
I could zoom out somehow, right? Now, this is a really nice thing about linear systems. If you look at any kind of a curve, like a parabola or a cubic or a square root or anything like that, if you zoom out, the look of that curve can change as you zoom, right? But not lines. Lines are the same on any scale. On any scale, a line is just a line, right? So if I don't see this right away when I hit zoom standard, don't mess around trying something just slightly bigger. Make the window huge. Go from like negative, let's set x minimum to negative 1,000 and x maximum to positive 1,000. And then don't bother with the y's. Never bother with the y's. Let the calculator figure those out. Once I set the x min and the x max, then I just go zoom 0, zoom fit. Let the calculator fit the y's to those. And so they still just look like lines, don't they, right? So really, I mean, if you want to, you could almost just skip right to that step every time, and then you'll never run the risk of not seeing the intersection. You'll always see it. As long as I can see the intersection, all I've got to do is just second calc 5, triple enter. Oops, there it is. That's it, right? Very simple. Okay? All right, try one. Try one on your own. Try that guy. Okay, so Jace, if I'm going to isolate y into the calculator for this top one, tell me exactly what I push on the calculator.
Parentheses.
Parentheses, good.
And punch in 15x was 50, or
Go start off with,
50.
I'm going to start with 57. Start with what already is over there, right? So we've done this. Whoops. We've done, essentially, we've just done that. Now what?
Plus, no, minus.
Minus, very good.
15.
Minus 15x. So we did this, right?
Right.
Good.
Parentheses.
parentheses, very good. And then,
Equals 15.
Equals,
I mean, divided by.
divided by 15, there you go, good, divided by 15. So then we just did that, right? Good. So there's the first one. Okay. Next one. Everett, what do I do for the second one?
19, or parentheses,
Parentheses,
19, minus 5x, parentheses, divided by 5.
divided by 5, good. Okay, and if I hit, we'll just go zoom 6 here. Ooh, what happened? Same line, yeah, huh? Same line. The red line just appeared right over the top of the blue line, didn't it? Right? Does that make sense? You got two different lines? Something must be, let's put something in. Oh, yeah, there you go.
So they must cross.
Okay, so, yeah, so now, there's one practical dilemma here, though. If you don't have the fancy color edition, you wouldn't have seen that line turn from blue to red. So how would you know that they're the same line graphically then? It'd be harder to tell, right? What you could do, though, wouldn't it make sense that if you turned the lines off one at a time and it looked the same, they'd be the same line? Does that make sense? So one thing you could do is you could go back up here and say, okay, well, if I unhighlight the equal sign, that turns that graph off. So if I turn off the first one and I get this line, now it would just look black on their other calculator, right? And then I go back to y equals, and now I'm going to turn first one on, second one off, and it looks the same, then it's the same thing. Now you got to be careful though. If you've got parallel lines that are really close to each other and you're on a really big scale, they might look like they're one on top of the other, right? So you got to be careful with that. One other thing you can do to guard against that, there's one other little trick here. I don't want to spend too much time on this, but if you want to zoom in on just one particular area, have I showed you guys the zoom box trick yet? Oh, this is pretty good. If you go zoom 1, zoom box, then it lets you define the window that you want to be enlarged. So I could go up here, for example, and go, like I could go, I'm gonna make that one corner of my box, and then I have to just drag out the opposite corner. So I'll start with that one, hit enter, and now watch what happens when I go down and over. I'm just dragging out a box, right? So then that's going to get blown up into the whole window, right? When I hit enter. So even when I zoom in, they still overlap. So those are the same line. That's the same line, isn't it? Right? Does that make sense? Okay. Practically speaking, wouldn't it be easier maybe just to multiply the bottom one by 3, though? You know, and just see that they. You know, those kinds of problems are always going to be pretty obvious, right? Yeah.
So on the other one, you said it was, no solution.
You want me to go back a little bit to that one?
You said no solution, so would this one be infinite?
Yeah, this one's infinite. You're right. It's
Like,
infinite. No, you're right. The one that we're doing now, because they're the same line, that's the answer. Infinitely
Okay.
many. Yeah, you're right. Mm-hmm. So this one is exactly like, Bailey, I know what you're asking. This one is exactly like that problem, isn't it?
Oh, I messed it up, sorry.
Does that make sense though?
Yeah.
'Cause and the reason it is, remember, is because if we could see this pretty easily, if I multiplied bottom one through by 3, I would just get the same exact equation, wouldn't I? Right. So that means that they're same line. Okay, and then what about this guy here? I'm going to do this one quick. I feel like I'm taking a little too much time on this. So top one, if we isolate y into the calculator, wouldn't I just get the quantity? I don't even have to put a 0 there if I don't want to. I can just add 8x to that side, right? And I end up with 8x divided by -8. bottom equation is already isolated for y. That's nice. If it's in slope-intercept form, then it just tells me what to put in there for y. So negative x plus 10. And if I zoom 6 this one, what's going on that time? Yeah, it looks like no solution. They look parallel. Could it be that they just look parallel, but they're going to cross way far out there? Possibly. How can I know graphically? Once again, this is the kind where if I plug that in, I'm just going to see pretty quickly that I'm going to get something that looks like the variables will drop out, and I'll get something like 0 equals 7 or something weird like that, right? A false statement. But graphically, how could I tell? I guess I could zoom way out, right? There's another way we can do this, though, that I want to show you. Another little trick on the calculator. We can ask the calculator what the slopes of these lines are. If the lines are truly parallel, what has to be true about their slopes? They have to be the same. So we could go second calc, and then the sixth option here is kind of a weird looking option. That's our calculus way of saying slope, though. So if we go second calc 6, and right now I'm on the blue line, so if I hit enter, it tells me that the blue slope is negative 1. If I go back and repeat that, second calc 6, and hit the up arrow to get to the red line, the red slope is also negative 1, so they're parallel, right? Okay. So all kinds of technology tricks we got today. All right, what about, let's just look at least one of these. So stuff like this. Quick review. You're going to see this kind of stuff on any standardized test you take. You can do a ton of this stuff like in chemistry. For sure, you'll do lots of solving linear systems in chemistry. Here's an example where we've got to build a linear system from a real-world situation. So how can we do a problem like this? We've got this. Teresa needs to rent a car. There's 2 car rental companies. Eagle Rent-A-Car charges a flat fee of $26.04 plus a 15-cent per mile mileage rate, right? The other rental company has no flat fee but charges 70 cents per mile for their mileage rate, okay? So they want to know after how many miles will both companies have charged the same amount, and how far, and what would that cost be? What would the break-even cost be, right? So how can I set this up? The first thing I've always got to do is identify what the variables are. The variables are the unknowns, and typically the unknowns appear where in the problem? They're the unknowns.
In the question?
In the question. Yeah, those are the questions, right? So they want to know after how many miles. So how many miles? Number of miles is one thing that's being asked about, right? And then what's the cost? So the cost is the other unknown that's being asked about. And those make sense as being the variables, aren't they, right? So then what if we let like x equal the number of miles and y equal the cost, right? We define those variables. And that's really the way we should do it, because if we're going to define our variables, which variable, x or y, do we want to be the dependent variable? If you go back to Algebra 1, I'm sure you guys talked about this a bunch. The y variable is going to be the output variable or the dependent variable, right? That's the one that should depend on the other one. Well, which makes more sense here? The number of miles driven depends on the cost, or the cost of the car depends on the number of miles driven? Well, second one, right? So the y should be the output or the dependent variable. I mean, it'd work either way, but it's going to be a lot easier this way. So now we've just got to come up with equations involving those variables for each situation. So let's just color code this. We'll say that Eagle Rent-A-Car is going to be our red equation. How do we say that? That the cost is going to be a flat fee plus a mileage rate of 15 cents per mile. Ah, okay. So y equals the cost, right, which is y, for the red situation, equals the mileage rate times the number of miles. Doesn't that make sense? It's 15 cents per mile times the number of miles driven, tells you how much you're paying for your mileage rate, plus the flat fee. Well, when they say something like a flat fee, what are they telling you?
The starting point.
It's the starting value, or the constant, isn't it? Because that's not gonna, no matter what, you go in there and you rent a car, you're paying that if you don't drive anything, don't drive anywhere, right? That's an upfront fee. What about the other company? Easy Rentals doesn't charge a flat fee, but charges 70 cents per mile, 77 cents per mile. So what's that gonna look like? Cost equals what? Yeah, 0.77x, and then there is no start value, it's 0, right? Okay, and then all I'd have to do is just graph those and see where they cross. Agree? Okay. What about something like that? Same kind of a thing. In this case, when a person buys 17 graphing calculators and 44 tablets, the total cost is that. When a person buys 33 graphing calculators and 20 tablets, cost is that. What are the variables going to be this time? AKA the unknowns. Okay.
How much each one?
Individual prices, yeah, that's what's being asked for, right? So we got the cost of a graphing calculator and the cost of a tablet. Very good. So if let's just define X as the cost of a graphing calculator and Y is the cost of a tablet. So then what's going to be the red situation? 17 graphing the red situation. Or 17 graphing calculators and 44 tablets cost $66.08. How can I write that as an equation? What's going to be the cost of 17 graphing calculators if X represents the cost of one graphing calculator? What if one graphing calculator costs $100? How much would 17 cost? How'd you get that? Oh, you multiplied by the cost of a graphing calculator, right? Well, we don't know what that is yet. That's X. So wouldn't the cost of the graphing calculators just be 17X? Right? So what's going to be the cost of the 44 tablets then? What's it going to be? 44Y, because Y represents the cost of one tablet. So 44 tablets times the cost of one tablet, and that total is 66.08, right? Compare that to the other situation where 33 graphing calculators and 20 tablets cost $56.32. So isn't that just going to be what, 33x plus 20y equals 56.32, right?
Yeah.
And then once we get to there, it's a piece of cake. Now it's just a linear system, right? And they just ask us to round what, to the nearest cent, so that's just the nearest hundredth of a dollar, right? So use your calculator and find the decimal answer, right? No big deal. Okay, so last part here. This is the part that's going to be a little bit new, and it looks complicated, but it's not. It's really not. So this is solving a linear quadratic system. So it's kind of one step up from what we just did. Here's a linear equation and there's a quadratic equation. How do we solve a system involving both of those? Well, the techniques are really the same. We could use, like in this case, what should we definitely do? What do you think? Substitute. Yeah, look, we've got this thing solved for y in the bottom equation. And which of the two variables in the top equation do we want to substitute in? Do we want to substitute something for x up there or something for y? There's a definite right answer here. Y. Yeah, for sure, y. If I were to solve for x here and I substitute it in up here, then I'm going to have to square out that whole quantity. I don't want to do that extra work, right? We want to substitute for the variable that's not being squared, right? So that's already done right there. Look, we've already isolated that variable y, so all I've got to do is plug it in up there, right? And then what do we get when we do that? Well, the left side is x squared. The right side is just going to look like x plus 2. And that's a little bit harder equation because it's quadratic, but there's only one variable there. And that's what Module 3 was all about, solving quadratic equations. So we're going back to Module 3. How do we solve that then? If we've got a quadratic equation, what do we have to do first? We want to solve it. It's a good opportunity to review.
I said square root.
No, can't square root. Because I don't have a single, remember, if I have a single x, then if I can point to a single x, then I can isolate it. But there isn't a single x up there, right? I've got an x squared and an x, so I can't just isolate x. What do I have to do instead? Remember? I gotta put this into a certain form, right? Oh, it's been a little while. Right, I gotta set it equal to 0. I gotta put it into standard form. So if I subtract x and subtract 2 from both sides, what am I going to get? Well, I'm going to get x squared minus x minus 2 equals 0, right? And now what? Okay, now I'm going to do two things. Either I'm going to look for magic numbers, or no, I can't do that. I can either look for magic numbers, or I can plug this into what every time? Quadratic formula. Okay. So maybe it sounds like it'd be useful to have those video solutions up to Module 3 for some of you guys? Okay, I'll work on that. Have a good weekend.